All right, hello. Just thought that I would go over the review questions 6.8, the review questions 2 to 9 that I had assigned in the Newton's 2 lesson. All right, let's go on. So, question number 2, use Newton's first law of motion to explain what will happen in each of the following situations. A car is trying to stop on an icy road. Well, Newton's first law of motion states that an object in motion stays in motion. And the whole point of taking a car on an icy road is that there's low friction. And so if we were to take a look and draw our car and consider the forces on there, so we're going to have the force of gravity. We're going to have a normal force. Now, is the object plowing into the ground or flipping up into the air? No. So these forces are going to be equal. And if those forces are equal, then they're equal and opposite. So the acceleration is going to be equal to 0 because we're dealing always with F net is equal to ma. So if the sum of the forces, in this case, so if the sum of the forces is equal to our F net, that's what we're always talking about, and that's equal to our mass times acceleration. Equal and opposite, no acceleration. They don't come into it. So the car is stopping on an icy road. All right. So what forces do we have acting on it? Well, we've got the force of the car going forward, right? No. And that's where Newton's first law of motion comes in. All we have is the force of friction going backwards. And if the force of friction is going backwards, that's the only force that's there. And if that's so low, the car has a hard time stopping. I've been in that situation. I've driven off the road because the road was glare ice one winter. Anyways, so car stopping on a icy road, it's going to stay in motion. It's going to slide right on through. When you're driving winter, always make sure that you are careful. A truck is going around a corner on an icy highway. Well, all right, same thing. But let's draw a picture overhead and not as a free body diagram so much. The last free body diagram sort of goes the same thing. All right, so here we have our truck, and here we have our cab of our truck. These are the windows. The truck's driving along. Well, the truck wants to go this way. But if we were to take a look at the wheels of the truck that go round and round, what forces have we got? Well, we have the force of gravity coming down. We're going to have a normal force going up. And we are going to have a force of friction as you turn the wheels that causes a force of a push towards the inside of the road. This is what's happening. There's a force that has to go towards the inside of the road for it to make this corner. And if the force of friction isn't there or is attenuated, then the force that's causing the truck to make the corner will be attenuated, in which case the truck is going to go off in a straight line. A force or an object in motion remains in motion, traveling in a straight line. It needs the forces of friction to make that corner. We have a passenger, similar situation. So now we've got a car, and we've got our passenger, and they're not wearing their seat belt. Well, the car suddenly comes to a stop. It hits an immovable motion. So the car is applying a force on the snowdrift. The snowdrift is applying a force on the car. The car is going to be having a force that is slowing it down in that direction. Well, this person just keeps on traveling. If the car is traveling 100 kilometers an hour, then the person is traveling 100 kilometers per hour. And so the person continues traveling in a straight line. and it will hit the window. Bad situation. All right. Airline passenger and a cup of coffee. All right. So here is our airline passenger, and here they are with their cup of coffee. Okay. So let's see if we can do this. Let's take these things. Oh, they are all as one person. That's what I want. Let's choose highlighter, and we're going to put our coffee. It's yellow coffee. Okay. All right. So you have, come back to our pen here. So we have the plane flying. Okay, so here we have the plane flying. Well, the plane suddenly hits air that is going down. And so what happens is that the plane drops down suddenly. So you can see if this works. So if we take this person and drop them down suddenly, what happens? Their coffee has remained, it wasn't connected with the passenger, with the seat. And so the coffee goes flying up and gets into the face of this person. They're not very happy. They're not very happy because now this coffee's hit them in their face. Now, I've found an image on the internet, and just so you can understand what's going on here, here we have 3 water balloons, and they were suspended by the tops. And then they shot it, looks like with a BB or BB gun. And so it hit the orange balloon first, hit the red one, and then hit the green one. Well, you can see barely any of the orange balloon. There is no rubber around there, and you can see the water starting to spray out. But the shape is still in the shape of what the water balloon was like. Same in the second one. You've got the rubber of the water balloon is contracting around it, but the water remains in shape. The water is not moving. There is the inertia that keeps the water there. And then the last one, the bullet or the BB's gone all the way through. You can see the edge of the water balloon beginning to contract. See this disturbance on the surface, but the water has not moved. This is inertia in action. And I mean, this is a high-speed camera. In a split second more, the water's all over the floor. In our plane, the coffee in the cup there's nothing keeping it in there. You'd need to be drinking coffee in a sippy cup, and then you would keep the coffee in there, in the cup. And the plane is dropped, the passenger is dropped, he's got the seatbelt on, and the coffee is in his face. That's what's happening there. All right, that was 2D. Now here on number 3, we've got Harry. Harry's pushing the car at 2 meters per second, and he's using a force of 243 newtons. What they're asking is, what's the road friction and air friction equal to in this situation? All right, so let's take a look again what's going on here. So we've got the force of gravity. You're going to hear me say a lot of the same things over and over again. Here, the car is not going into the ground, is not flying up out of the ground, which means that our F net, which is equal to our force of gravity plus our normal force, has to be equal to our mass times acceleration, which is equal to 0. Because it's not accelerating up or down, then these forces have to be balanced. And so the force of gravity is equal to the force normal. And there's no acceleration up or down. We don't care. He's pushing it at 2 meters per second. So there is a force of a push that's going on with 243 newtons. Well, is it accelerating horizontally? It's got this 2 meters per second, but that's a velocity, that's not an acceleration. And so that means that, again, if our we have a velocity and acceleration. Our acceleration is going to be equal to 0, so our net force, and we can say horizontally, also has to be equal to 0. And so we're going to have a force of our push, so let's say our net force, and we're going to have a force of our push plus the force of friction has to be equal to 0. This is 243 is equal plus our force of friction is equal to 0, which means our force of friction is equal to negative 243 newtons. And that just means that it's going backwards. So that means the force of friction is equal to the force of the push, which is equal to our 243 newtons in terms of the magnitude, the size of the forces. So here we have our force of friction, obviously in the opposite direction, but it's also 243 newtons. All right, let's go to question number 4. We've got a 5.5 kilogram grapefruit, and we're accelerating it at 4 meters per second squared and at 8 meters per second squared. I'm just doing these two. You can do the other ones and just make sure that you are correct. So our mass is equal to 0.5 kilograms, and we have an acceleration which is 4.0 meters per second squared. And we want to know what's the accelerating force. All right, so we just have F is equal to ma. And so we'll have a 0.50 whatever kilograms times our first acceleration, which is 4.0 meters per second squared. 0.5 times 4, that's equal to 2 meters per second squared. Oh, sorry, 2 newtons. That's the force that is required, the accelerating force required to accelerate our grapefruit at 4 meters per second squared. Likewise, if we put in for B, the 8, we're going to have 0.50 kilograms, and it's accelerating at 8 meters per second squared, and that's going to be equal to 4.0 newtons. We've doubled the acceleration. We're going to double the required force in order to add this. I seem to have a message, but we'll deal with that in a bit. All right, that's number 4. Let's go to number 5. So again, here we're dealing with the situation F equals ma, and so we'll take away 1, give us the other 2, and calculate the third. So here we have an 84 Newton force and 4.2 kilograms and 8.4 kilograms, and I'll leave the 12.6 kilograms to you. All right, so our force is equal to 84 newtons. Our mass is equal to 4.2 kilograms, and we're looking for the acceleration. F is equal to ma. We do our algebra first. A then is equal to our force divided by our mass. So in this case, we'll take our 84 newtons, divide that by our 4.2 kilograms, and our acceleration in this case comes out, this is question number 5, just finding my notes, at 220. No, 2022. I can't even read my writing. Yeah, 20 meters per second squared. And if we do the next one, F is over M. So we have 84 newtons divided by 8.4 kilograms, and that's equal to 10 meters per second squared. There's our solutions. All right, number 6. A 1,200 kilogram car traveling at 50 kilometers per hour has an air resistance of 5,000 newtons, road friction of 2,000 newtons, and the wheels are pushing with 7,500 newtons. What is A? This is really bringing in the idea of our F net and that the sums of our forces. This is summation. The sums of their forces are equal to our F net, and that's equal to our total mass times our acceleration. So we have our mass of 1,200 kilograms. We're told 50 velocity is equal to 50 kilometers per hour. Why do they tell us? It just tells us that the acceleration is equal to 0. And so if that F net just means our net force, then it's going to be equal to 0 as well. Right, so we have road friction. Let's go FFR. That's equal to 2,000 newtons. We have the friction of air. That's equal to 5,000 newtons. And then we have the force of the wheels, of the push. And that's equal to 7,500. Getting all these notices. I'm sitting here all day, nobody talking to me. I do a video and start getting notices. All right, so let's draw our picture. There's our car. Everyone's talking to me. All right, so we're going to have force of gravity. We're going to have a normal force. But again, it's not plowing into the ground. It's not lifting up into the air, which means that the normal force, the acceleration is going to be equal to 0, so the normal force and the force of gravity are going to be equal to 0. These forces, I'm including them. They don't come into the question, but I'm including them. What other forces do we have? Well, I'm doing it to this the wrong direction, but that's okay. So I'm going to have a force of friction, which is going opposite to our motion. That's 2,000. We're going to have the force of the air friction, which I call F air, and that's equal to 5,000. And then we have the force of the push, and that's equal to 7,500 newtons. So what we've got here is unbalanced forces. What is A? So A is not equal to 0, but this is just our initial velocity. Strange question. Anyways, they give us, we don't have to use this. Anyways, so coming into here, what we have is we have forces going in different directions. So what we need to do is we need to assign a direction that's going to be positive. So let's take that direction to be positive. And so we want to take a look at the sums of our forces, and that's what we're saying is our F net. So what forces do we have? Well, we have the force of our push, we have our force of friction, and we have our force of the air friction. And that will be equal to our mass times our acceleration. So what's the force of our push? Well, that's equal to 7,500 newtons. We should probably say this is a negative friction and negative air. So we have a force of friction that's negative 2,000 and 5,000. And a negative 5,000 newtons. And so this is equal to 7, so this is going to be 500 newtons is equal to our mass times A, and our mass is 1,200 kilograms, and we're looking for A. And so when we solve for A in this, did I mess something up? Yeah, I did. I said this was 2,000, it was 2,200. You probably already noticed that. Sir, what are you doing? All right, so this is 2,200, so this becomes to be 300. A is then 300 divided by 1,200, and that's equal to 0.25 meters per second squared. I know you're probably yelling at me, and I just couldn't hear you. Speak up. All right, let's continue on. You can always pause these things to take a look at them or go back over them. Question number 7. We have a 1,100 kilogram car and it's accelerating at 3.40 meters per second squared. The wheels push with 5,600 newtons. What is the resistance force? And again, we're bringing in the idea that the sums of our forces is equal to our what we call our net force. These mean the same thing, and that's equal to our mass times our acceleration. All right, so what have we got here? So we're going to have a force of gravity. We're going to have our normal force. Is it going into the ground or flying up into the air? No. So these are going to be equal and opposite to each other, and we're not going to care. We have the wheels that are pushing the car ahead of 5,600 newtons, and then we have some sort of force of friction that's going in the opposite direction. All right, so if we say this direction is positive, our net force then, we're going to have 5,600 newtons plus a negative force of friction. I really prefer using a negative force of friction, negative forces, rather than subtracting. Subtraction is the same thing, so you go 5,600 minus the force of friction. I like the negative sign here because it lets me know the direction of the friction's opposite. Our mass then is 1,100 kilograms, and our acceleration is 3.40 meters per second squared. So what's going to happen is we're going to have our 5,600 newtons. This is going to come over to that side. That's going to go to that side. So here we have a negative 3740. Now we call our force of friction. And so then our force of friction is equal to 1860 newtons. And it's going in the opposite direction. And we're good. Now you're saying, but where's the negative sign if it's going the opposite direction? Well, we defined the force of friction with negative values. This is just telling us the value of the force of friction, which we know is going in towards the left, has a positive value of 1860 towards the left. Question number 8. We have two boys on ice, 60 kilograms and 90 kilograms. One's a bully. He pushes the other boy with 360 newtons for 0.1 seconds. Well, what's the acceleration? What's the velocity? And does it matter who pushed? Let's start with this one here. The answer is no. And that comes to Newton's third law of motion, that when you push in one direction, well, you're being pushed in the opposite direction with the same amount of force. Now, the acceleration and velocities are going to be different. But yeah, and so why do we say this on ice? Because that tells us no friction. And that just makes it easier to calculate things. All right, so we know that our force is equal to 360 newtons. We know the mass is either 60 or 90, and we want to know what the accelerations are. All right, so F is equal to ma. So we know 360 newtons is equal to our mass. Let's take our 60 kilogram boy and times acceleration. The acceleration for that boy then is 6 meters per second squared. Likewise, for the other one, 360 newtons is equal to 90 kilograms times A. A comes out to be 4.0 meters per second squared. These are the accelerations that the two boys would feel. All right, so then it asks, well, what are the velocities? All right, so our initial velocity is equal to 0. Our acceleration is given. Our time is equal to 0.1 seconds, and we want to know our final velocity. Well, that tells us v is equal to v naught plus at. Kinematics is something that continues to happen throughout the course. So you can't forget your kinematics. Excuse me. It always can come up. All right. So velocity is equal to 0 plus We have our 6.0 meters per second squared times it by 0.1, and that's going to equal 0.60 meters per second. Likewise, if we put this in for the next one, we have 4.0 meters per second squared times our 0.1 seconds. That's equal to 0.40 meters per second. And there we have our two velocities of the boys. All right, final question, question number 9. We've got a 6 kilogram block on ice traveling at 12.5 meters per second. There is a frictional force of 30 newtons. What is the acceleration? And how long does it take time to stop? All right, so we know our mass is 6.0 kilograms. Velocity 12.5 meters per second. Force of friction is equal to 30 newtons. All right. Let's draw a picture. Force of gravity going down, normal force going up. Yes, we are not using these forces, and yes, we recognize they are the same. Do we need to draw them? Yeah. Do we have a force moving the puck? And the answer is no. An object in motion remains in motion, traveling in a straight line. What we do have is a force of friction going in the opposite direction. So, F is equal to ma, our net force. Our net force is going to be our force of friction then. Our mass, which is 6.0 kilograms. I'm not sure what I was going to say. And our acceleration, well, that's what we're trying to find. Our force of friction, we're told, is equal to 30 newtons. Our acceleration then, 30 divided by 6, is going to be equal to, it's going to be equal to 5 meters per second squared. And the thing is that it's going to be going in that direction. So that gets us the acceleration. So secondly, we want to get the time to stop. Well, here we're going to be using v is equal to v naught plus at. V is going to be equal to 0. This is going to be 12.5 meters per second squared, plus our acceleration times our time. Sorry, time to stop. There we go. The acceleration then is going to be, so a negative 0 is equal to 12.5 plus a negative 5.0 times t. So we're going to have, this is negative 12.5 on the left-hand side, divided by negative 5.0 from the right-hand side. That's equal to my t. And when I do that calculation, t is equal to 2.5 seconds. All right, there we go. There is that's question number 9. That was your homework. Hopefully that has helped if you have had some questions. All right, take care.